Hello guys, welcome to Self-Help Maths Academy. Today we are going to discuss about the Rolle's theorem and we will verify the Rolle's theorem for some certain examples. The geometrical interpretation of the Rolle's theorem, already we have done the video and I have it. You can just check it there. So here I'll just discuss the statement and I'm going to discuss about the how do we verify the examples. All right. So now let's start with the statement. So here the statement says that a function f is defined on the closed interval ab, okay, then it is continuous in the closed interval ab, and the given function is derivable in the open interval ab, okay, and the third condition is f at the point of a is equal to f at the point of b. If all these three conditions are satisfied, then there exists a real number c in between the open interval ab such that our derivative at that point is equal to 0. So basically, when we have a function in the closed interval ab, our function is continuous. It should be continuous in the closed interval. It should be derivable or differentiable in the open interval ab, and the endpoints function at the endpoint should be equal. If three conditions are satisfied, then we have some c in this open interval ab such that our derivative at that point is equal to 0. That is the basic understanding of the Rolle's theorem. All right. So now I think we are good with the statement. So let's check directly with the examples wherein we'll be verifying our Rolle's theorem for certain examples. All right. So how do we verify the Rolle's theorem? So let's see. Let me start with the example. Verify the Rolle's theorem. Rolle's theorem for the following functions. For the following functions. For the following functions. Okay. Let's see what is our first function we'll be understanding, and we'll be taking up the examples. Let's see. Let me take one example where our f of x is, let me start with f of x equal to x square minus 6x plus 8 in the interval 2, 4, the closed interval 2, 4. Let's verify our Rolle's theorem for these functions. So basically for this, as you know, we have to check. First condition is it should be continuous in the closed interval and it should be derivable in the open interval, and f at the point of 2 should be equal to f at the point of 4. If these three conditions are satisfied, then we have to search for some c which belongs to this interval, and we have to see that our derivative at that point whether it is equal to 0 or not. Okay, let's see. Let's verify that thing. Now if I see, look at the function. This function is a polynomial of degree 2. This function is a polynomial. Okay, basically f of x is a polynomial. It's a polynomial, and we know that a polynomial is continuous function. It's a polynomial, whatever the order it may be, the polynomials are basically a continuous functions. So therefore we can say that the first condition, this function, therefore since it is polynomial, it is continuous. It is continuous. That is our first condition. It is continuous in the closed interval 2, 4. Okay. Second condition is we should check that it is differentiable. Let's see. Let me take f dash of x. So x square minus 6x plus 8 is our function. So the derivative of this function x square will be 2x. 6x derivative is 6 and derivative of the constant is 0. So it is simply 2x minus 6. Okay, this exists. this is exists for every x belongs to the open interval 2 comma 4. Okay, so therefore here it is the derivative exists for every open interval x belongs to 2 comma 4. All right, so this implies what? This implies our f of x is derivable. F of x is derivable in the open interval 2 comma 4. So both the conditions are satisfied. Now third condition. Third condition is, let us check f at the point endpoints f at the point of 2. So it will be, since our function is x square minus 6x plus 8, so wherever x is there put 2. So 2 square minus 6 into 2 plus 8. This is 4 minus 12 plus 8. So 12 minus 12, which is 0. Okay. Similarly, let us check f at the point of 4. So this is simply 4 square minus 6 into 4 plus 8. This is equal to 16 minus 24 plus 8. This is 24 minus 24. Again, it is equal to 0. So clearly what we have here, f of 2 is equal to f of 4. So all the three conditions are satisfied. The given function is continuous in the closed interval 2 comma 4, and it is differentiable in the open interval, and f of 2 is equal to f of 4. So all these three conditions are satisfied. Hence we can write here, therefore f of x satisfies all the three conditions of Rolle's theorem. Conditions of Rolle's theorem. If it satisfies three conditions, it says then there must exist at least one c belongs to the open interval 2 comma 4 such that f dash of c should be equal to 0. Okay, but what is our f dash of x? We have found f dash of x is 2x minus 6. So therefore wherever x is there, let me put a c. So let me put the c. So since we know f dash of x is 2x minus 6, so f dash of c will be 2c minus 6 equated to 0. This implies 2c equal to 6. Dividing both the side by 2, you will get c equal to 3. C equal to 3. Obviously this 3 belongs to the open interval 2 comma 4. So this if you take 2, this is 4. So your 3 belongs to where? 3 belongs to this open interval. Okay, this 3 belongs to the open interval 2 comma 4, right? So hence the Rolle's theorem verified. Rolle's theorem is verified. Okay, so this is how you should verify the Rolle's theorem. Okay, so like that, maybe I think I'll give a simple example here for you to try. So you have to try and let me know whether this satisfies the Rolle's theorem or not. So if I give you 8x minus x square in the closed interval 2 comma 6. So, and also please try this one also. Let me take f of x is equal to x cube minus 4x. It is in minus 2 comma 2. Okay, so just check whether these two examples are the Rolle's theorem will be verified with respect to these two examples or not. All right, so now let me take another example. It is like, say, f of x is defined as x square plus 1 for your 0 less than or equal to x less than or equal to 1, and it is equal to 3 minus x for 1 less than or equal to x, which is less than or equal to, say, 2. Okay, so this is our given function. Now let us understand this function, and then we will see whether all the conditions are satisfied or not. So here f of x is defined on the closed interval 0 to 2. If you observe, it is between 0 to 1 and between 1 to 2. So basically we are defining a function between 0 to 2. Okay, so it is defined on the 0 to 2. So in particularly f of x is x square plus 1 if it is in the closed interval 0 to 1. Okay, and which being a polynomial. If you see, x square plus 1 is our polynomial, and basically the polynomial functions are derivable. As I told you, this is derivable and continuous for all x belongs to the closed interval x 0 comma 1. Okay, also let me write it here. So basically f of x is equal to x square plus 1. This is for 0 less than equal to x less than equal to 1. This is which is being a polynomial, which is being a polynomial. This is being a polynomial. Okay, polynomial is continuous, and derivable, continuous and derivable for all x belongs to the closed interval. Let me write it here. For all x belongs to the closed interval 0 comma 1. Okay, let us erase this one. Okay, and similarly also your f of x is 3 minus x. Your f of x is equal to 3 minus x for 1 less than equal to x, which is less than equal to 2, which again being a polynomial, which is being a polynomial, which is being a polynomial, is continuous, and again derivable, continuous and derivable for x belongs to the closed interval 1 comma 2. Okay, so because both are polynomial, this is a polynomial of order 2, this is a polynomial of order 1. So now since you're in here, what happened, the domain of definition is partitioned. If you see, the domain of definition is partitioned at x equal to 1. At x equal to 1, our domain of definition is what? Partitioned, while defining our f of x. So we are not sure, because our the I'll just write it since the domain of definition, is partitioned, what where? At x equal to 1, while defining f of x. Okay, so therefore we are not sure what at x equal to 1, we are not sure about whether the continuity or derivability at x equal to 1. So therefore we need to check at remaining all the sides we are good with. So what we have to do, we are not sure here, we are not sure about the continuity, and derivability, at what point? At x equal to 1. Okay, so because it is it is the domain of definition is partitioned, so hence what we have to do, we have to check the continuity as well as the differentiability at that particular point. So what I'll do, let me check now the continuity for x equal to 1. Now we will check the continuity at x equal to 1. So for that, let me take the LHL, that is limit as x is tending to 1 minus 0 f of x. So as x is less than 1, how it is defined? X is less than 1, the given function is x square plus 1. So let us take that one, limit, this is x square plus 1 as x is tending to 1 minus 0. Okay, so this is equal to, so here what happened, your x is basically at x equal to 1 I am checking, so you should put x equal to 1 minus h. So therefore this becomes what? 1 minus h the whole square plus 1. Then limit, this is as x tends to 1, this is h tends to 0. Okay, so this will be now the given function. So if you just simplify this one, this will be equal to limit as h tends to 0. This is 1 plus h square minus 2h plus 1. Okay. So here we have got 2 plus h square minus 2h. So it is basically as h tends to 0, this term becomes 0, this term becomes 0. It is simply what? We will get here 2. Okay. Let me take the RHL now. RHL. So this is limit of f of x as x tends to 1 plus 0. So as x is tending to greater than 1. So greater than 1 in the sense your function is here 3 minus x. That's how it is defined. So let's take that as limit x tends to 1 plus 0, that is 3 minus x. Okay, so again for right hand side function, put x is equal to 1 plus h. So this will become limit h tends to 0. This is 3 minus 1 plus h. Wherever x is there, put this will be now limit as h tends to 0. 3 minus 1 is 2. 2 minus h, as h tends to 0, it is 2. Okay, as I put h equal to 0, this is equal to 2. Okay, so hence what we have got now, LHL and RHL both are equal to 2. So let me check the limit at x equal to 2 now. Limit of f of x as x tends to say 1, what happens to the given function at exactly x equal to 1. If you put I mean it is basically you're checking your function at f at the point of 1. Okay, so that will be like checking the given function at x equal to say 1. So if you put x equal to 1, so less than or equal to 1 is you have. So as x is 1, so 1 square plus 1, that is equal to 2. Okay, so you'll be having here, if you see this, whether you take this function or this function, 3 minus 1, it still give you 2. This also will give you 2. So therefore let me take f of this is nothing but f at the point of 1. Okay, so this is nothing but 2. All right, so therefore it holds all the conditions. Hence LHL is equal to RHL, which is equal to f of 1. Hence f of x is continuous. F of x is continuous at x equal to 1. So no problem, at x equal to 1 the continuity holds. So let's check the derivability. For that we have to and now for the derivability, let me check the left hand limit. This is equal to limit f of x minus f of 1 upon x minus 1 as x tends to 1 minus 0. This is equal to, so this is limit as x tends to 1 minus 0. F of x as x is less than 1, so this will be like x square plus 1 or function, and f at the point of 1 already we calculated, that is 2, upon x minus 1. Okay, so now since it's the left hand limit, so put x equal to 1 minus h, where h is greater than 0, right? So therefore what we will get here, a limit, this is 1 minus h the whole square plus 1 minus 2 upon 1 plus 1 minus h minus 1. This is as h tends to 0. So let us find the value of this. This is like 1 plus h square minus 2h plus 1. This is minus 2 here, this one, divided by minus 1 plus 1 cancels, it is negative h. Okay, so here plus 1 is plus 2 and minus 2, this cancels. So here what we in the numerator we can take h out. So this will be h minus 2 upon negative h. So this h also cancels. Limit as h tends to 0. As h tends to 0, this will be like simply negative 2 upon negative 1, which is equal to 2. Okay, so this is what we get. So the value of the left hand side limit is 2. So similarly, let us find out the right hand limit. For the right hand limit, limit of, by the definition, f of x minus f of 1 upon x minus 1 as x tends to 1 plus 0. Okay, so this is equal to what is our function at x greater than 0? So the function is 3 minus x. This is 3 minus x. F at the point of 1 is 2, and this is x minus 1. Limit as x tends to 1 plus 0. So since it is a right hand limit, so put x equal to 1 plus h. Okay, so this will be equal to, limit changes as x equal to 1, h tends to 0. This will be now 3 minus 1 plus h, okay, minus 2 upon 1 plus h minus 1. Okay, so this is equal to limit as h tends to 0 plus. So this will be now 3 minus 1 is 2, and this is minus h. So 2 minus 2, which is equal to 0. So it is simply minus h here. This cancels, divided by h. So h also cancels, and just it is simply negative 1. Okay. So here what we have got, the RHD is negative 1. So therefore LHD is not equal to RHD. So hence the given function is not derivable. Therefore f of x is not derivable at x equal to 1. So it is continuous at x equal to 1, but it is not derivable at x equal to 1. So therefore f of x is not derivable at every point of the open interval. Okay, so this implies what? This implies f of x is not derivable at every point of the open interval 0 comma 2. So we are supposed to have that condition, right? It is continuous at every point in the closed interval 0 comma 2, but it is not derivable at the every point at the open interval of 0 comma 2. Therefore f of x does not satisfy the condition. The second condition itself is not satisfied. Condition of derivability in the open interval say 0 comma 2. Okay, so therefore what happens? The Rolle's theorem is not applicable to f of x in the closed interval 0 comma 2. Okay, so that means what? Since the second condition itself fails, so therefore we will not go further in order to check the to verify the Rolle's theorem. So it is not applicable in the second condition itself. It is not derivable. It is continuous. The first condition holds, but the second condition does not holds. Okay, so therefore the Rolle's theorem fails. Okay, let me take another example now, that let us have the function f of x equal to x into x minus 3 the whole square. It is on the closed interval say 0 comma 3. Let's see. So here basically given function is f of x is equal to x into x minus 3 the whole square. So let us write it now in the proper format. This is nothing but x into, it is in the form of a minus b the whole square. We know a minus b the whole square is a square plus b square minus 2ab. So let us write this: a square plus b square is 3 square, that is 9, minus 2a into b. Okay, so this is equal to x into x square plus 9 minus 6x. Now just multiplying with x inside, it will be x cube plus 9x minus 6x square. So our f of x is basically x cube minus 6x square plus 9x. Now this is our function. F of x. This is defined in the closed interval 0 comma 3. Okay, this is defined in the closed interval 0 comma 3. So when I look at this function being a polynomial, this is a polynomial. So therefore given f of x is polynomial. So when it is a polynomial, we know that it is continuous. Okay, it is continuous. Therefore f is continuous. f is continuous in the closed interval 0 comma 3. Okay, and this is true for all the x. So also f is derivable. F is derivable in the open interval 0 comma 3. Also let me check. Also this is the first condition, this is the second condition. Also let us check f at the point of 0. What happens? This is 0 minus 6 into 0 plus 9 into 0, which is 0. And similarly let us find out f at the point of 3. This is 3 cube minus 6 into 3 square plus 9 into 3. This is equal to 27. Then we have got 3 square, f at the point of 3 is 3 cube. Then this is 954. This is again 27, which is again 0. So clearly f of 0 equal to f of 3 equal to 0. So they are 0. Thus all the three conditions are satisfied, right? All the three conditions of Rolle's theorem are satisfied. So when all the three conditions are satisfied by the Rolle's theorem, there exists at least one value c of x in the open interval 0 comma 3 such that our f dash of c must be equal to 0. So first let us find out what is our f dash of x. So f of x is x cube minus 6x square plus 9x. So let me write the f of x, then let me write f of x is x cube minus 6x square plus 9x. This gives us f dash of x as 3x square minus 12x plus 9. So therefore, let us find out f dash at the point of c. This is 3c square minus 12c plus 9, equated to 0. Okay. So let us find out the value of c. So here clearly, in this, we can take this 3 out completely. This will be c square minus 4c plus 3. This is equal to 0. So 3 cannot be 0. Hence c square minus 4c plus 3 must be equal to 0. Now after multiplication I should get 3. After addition or subtraction I should get negative 4. So I can take the factors as c square minus 3 c minus c plus 3 equal to 0. So here I can take c out, the c minus 3 plus 1, here negative 1 I worked, this will be c minus 3, which is equal to 0. So c minus 3, c minus 1 equal to 0. This implies c equal to 3 or c equal to 1. So we have got a c equal to 3 and c equal to 1. So out of this c equal to 3 and c equal to 1, we know that this 3 cannot be belongs to the open interval 0 comma 3, right? 3 cannot belongs to the open interval 0 comma 3. So therefore the remaining value is what? 1. This belongs to 0 comma 3. So hence we have got one value which belongs to the open interval. Therefore we say that hence the Rolle's theorem is verified. The Rolle's theorem is verified. Rolle's theorem is verified. Okay. Now let's start with another example. One more example let me take, where we'll verify the Rolle's theorem. Given function is f of x equal to, say, x cube minus 6x square plus 11x minus 6 on the closed interval 1 comma 3. Okay. Okay. Now the given function, if you see, this is a polynomial function. So hence what we say, which exists for all the, like continuity for derivability exists. So you can write here, given, let me write it, given f of x is a polynomial. It is a polynomial. Therefore, the first condition, therefore f of x is continuous for all the x, including the closed interval 1 comma 3. Second is f of x is derivable. F of x is derivable in the open interval 1 comma 3. Okay. Then let us check f at the point of 1. This is 1 cube minus 6 into 1 square plus 11 into 1 minus 6, which is 1 minus 6 plus 11 minus 6. So this is 12 minus 12, which is equal to 0. Similarly, f at the point of 3. This is 3 cube minus 6 into 3 square plus 11 into 3 minus 6. This is equal to 27 minus 9. This is 54 plus 33 minus 6. So this is 72. I mean, yeah, 72, and here it is. Let me check here. I think, okay, minus 6. So what we have got here, this is 33, and this I think, yeah, it's 60 and 60 is, which is equal to 0. So we have got f of 1 equal to f of 3, which is equal to 0. So these three conditions are satisfied, right? So hence all the three conditions are satisfied. Therefore, we can say that thus all the three conditions of Rolle's theorem are satisfied. Therefore there exists at least one value c of x in the open interval 1 comma 3 such that f dash of c should be equal to 0. So let us write f of x again. F of x is x cube minus 6x square plus 11x minus 6. Find out f dash of x. So this will be equal. So here basically this is 3x square minus 12x plus 11. This is your f dash of x. So our f dash of c will be 3c square minus 12x plus 11 equated to 0. Okay. So this is what we have to equate it to 0. Now this, if you see, it is like a quadratic equation where if you see this, I'll take as a equal to 3, say b equal to minus 12 and c equal to 11. Then our to find out the value, we'll use this one. So here let me this take as c. So x is equal to minus b plus or minus square root of b square minus 4ac upon 2a. Let me use this one. So here in place of b I have negative 12. So plus or minus square root of minus 12 the whole square minus 4 into a into c, that is 11. Okay, divided by 2 times of 3. Okay, so this is equal to 12 plus or minus square root of we have 144 plus 12 into 11. Let us see what happens to 12 into 11. That is, okay, 132. Yeah, divided by 6. So here you will be getting this as, if I simplify, this is 12 plus or minus square root of, this will be like 6, 7, 276 upon 6. So after simplification you will get your c as 12 plus or minus 2 root 3 upon 6. So this is basically, if you get dividing by 6 means here it is 2 plus or minus 1 over root 3. Okay, 1 over root 3. Okay, yeah, 1 over root 3. Okay, so if you calculate this, it is 2 plus or minus 0.57. This is either 2.57 or 1.43. Okay, so here clearly if you see that this both these values lie in the open interval 1 comma 3. Okay, so therefore C is equal to 2 plus or minus 1 upon root 3 exist such that our f dash at the point of C will become 0. Hence the Rolle's theorem hence the Rolle's theorem is verified. Hence the Rolle's theorem is verified. Okay, so this is how, guys, we will be actually verifying the Rolle's theorem for a different example. I think I'll give you some examples. Please verify the Rolle's theorem for that, and you can just give your answers in the comments, whether you get the Rolle's theorem to be verified or not for that particular functions on the closed interval 0 comma 1. Please check this one, and also check f of x equal to say square root of 1 minus x square on the closed interval minus 1 to 1. Okay, so I think this is all in this video, guys. So we have done the verification on the Rolle's theorem. Maybe in the next video we will verify our mean value theorem. Okay, I think this is good. So just please leave your comments whether it follows the verify, I mean, like, it follows the uh, Rolle's theorem or not, and get back to the comments. Okay, with this, let me conclude, guys. See you all in the next video. Bye bye, guys.